Hello and Salam Sejahtera. I'm Jana Ibrahim. This is an introduction to BJT AC signal analysis. A signal carries some type of information. For example, human voice is a type of sound wave signal. The magnitude of an analog signal can take any value and may vary continuously over time. A linear amplifier magnifies the input signal and produces an output signal whose magnitude is larger and directly proportional to the input signal. The transistor is the main part of an amplifier. BJT has been used in linear amplifier due to its relatively high gain. In this video, we will discuss the common emitter AC signal circuit. The AC characteristic of a common emitter amplifier are demonstrated using its equivalent circuit. The equivalent circuit is also used in many AC calculations. To conduct AC analysis on the linear amplifier, we can apply superposition principle, which means for any given circuit, DC analysis is performed by AC source turns off or set to 0, and AC analysis is performed with DC source set to 0. The figure shows a BJT circuit with an input signal VI contains both DC and AC signals. VBB here is the DC voltage to bias the BJT at the particular Q point, and Vs is the AC signal that needs to be amplified. The voltage transfer characteristic shows that the BJT is biased with a Q point that is in a forward bias region. If the AC signal is superimposed on the DC biasing voltage VBB, the output voltage will change along the transfer curve, producing an AC signal output voltage. And if the output AC signal is directly proportional to and larger than the input AC signal, then the signal is amplified and the circuit is a linear amplifier. However, if the AC signal is not properly biased or the Q point is near to the cutoff or saturation regions, the AC output voltage does not change with the change of the input voltage. So, the circuit is no longer a linear amplifier. In this video, we will discuss the AC signal analysis. At first, we need to consider the AC representation that will intuitively describe the basic operation of the BJT towards AC signal. Here we need to develop the AC signal equivalent circuit that will be used in the analysis. In general, we are considering a steady-state sinusoidal analysis. The AC signal can be written as a sum of sinusoidal signals with different amplitudes and frequencies. Note that the signal total instantaneous values consist of DC and AC components. The lowercase letters represent AC signal, while the uppercase letters represent the DC values. Here is the current voltage characteristic of the previous inverter circuit. We can see that the AC source Vs will produce the AC base current IB superimposed on the IBQ, and the AC collector current IC is superimposed on the ICQ. The AC current IC then produces an AC voltage across RC and induces the collector emitter AC voltage. To start our analysis, the superposition technique is applied to linear amplifier circuit, which means the DC and AC analysis can be performed separately. However, to obtain a linear amplifier, The AC current and voltage must be small enough to ensure a linear relation between the AC signals. In other words, the amplitudes of the AC signals must be small enough to get a linear relation. This figure shows the exponential relationship between base current IB and base emitter voltage VBE. If the magnitude of the AC signals superimposed on the DC cue point are small enough, we can develop a linear relationship between the AC BE voltage VBE and AC base current IB. And the slope here, or the slope of the curve at cue point, corresponds to the relation of IB and VBE. From the concept of small signal, the time-varying signals can be written as the time-varying base current IB is equal to IBQ plus IB AC signal. IC time-varying signal is equal to ICQ plus IC AC signal. VCE time-varying signal is equal to VCEQ plus VCEAC, and VBE time-varying signal is equal to VBEQ plus VBEAC. If the signal source Vs is equal to 0, the BE loop is left with the DC values. And by applying the superposition method, by setting the DC current and voltage equal to 0, that is, DC voltage sources become short circuit and DC current sources become open circuit, this will result in the AC equivalent circuit. In the AC equivalent circuit, all currents and voltages are in time-varying signals, and we still assume that the BJT is biased in the forward active region. The hybrid pi model shows that the input base emitter terminal is represented with R pi, and we can see that the VBE is equal to IB times R pi. R pi is the diffusion resistance or base emitter input resistance, and R pi is the function of cue point parameter, that is, R pi is equal to Vt over IBQ or beta times Vt over ICQ. Meanwhile, the output collector emitter terminals is represented by a dependent current control source, and the value is equal to Gm times VBE. The small signal current at collector emitter is IC, and therefore Gm times VBE is equal to IC. Note that the transconductance Gm is equal to ICQ over Vt. The Gm is also a function of cue point parameter and directly proportional to the DC bias current. The current control source Gm times VBE can be used interchangeably with beta times IB. Earlier, we have discussed about the early voltage effect, where the collector current does vary with collector emitter voltage VCE. Therefore, if we consider the early effect condition, there will be a resistance at the collector emitter terminals RO, which is called the small signal transistor output resistance. And RO is equal to VA over ICQ. This resistance can be thought of as an equivalent to northern resistance, where RO is in parallel with the dependent current source. Then, we can redraw the inverter circuit with the hybrid pi equivalent circuit. Previously, we have discussed many amplifier properties, including gain, input impedance, and output impedance. There are three types of gain, namely the current gain AI, voltage gain AV, and power gain AP. Under normal circumstances, the common emitter exhibits all three types of gain. In contrast, the common collector amplifier provides only AI and AP, while the common base amplifier only AV and AP. Therefore, it's up to the circuit designer to choose the type of amplifier configuration that suits the desired gain. Since common emitter can provide all three of gains, it is the most oftenly used amplifier configuration. The input and output relationship of the common emitter amplifier is unique, as its input and output signal voltages are 180 degrees out of phase. Once we have transformed the common emitter circuit into its AC equivalent hybrid pi model, we can determine amplifier parameters mentioned earlier in our next video. That's all for now, and see you again in my next video.